prove that the closure of S is the set of all limits of sequences of points of S that converge in E. And this E is the metric space in which S lives. So S lives in the metric space E. So let me rewrite this statement in a little bit of a different way so that we can get a firmer grasp of what they're asking. So we want to show that the closure of S is equal to the following set. Is the following set, or in other words, is equal to the following set. All points P such that P1, P2, P3, and so on is a sequence in the set S such that the limit of this sequence is equal to P. So that's the same as saying the set of all limits of sequences of points of S that converge in the metric space E. So we want to show this set equality. Remember, to show set equality, we have to do two things. We have to show that the left side, that is the closure of S, is a subset of this right side, which I'm going to call this set, for short, I'm going to call it L. I'm going to call this set L. So we want to show that the closure of S is a subset of L. And then we also want to show that L is a subset of the closure of S. We're first going to prove that the closure of S is a subset of L. Now, we're going to prove this by contradiction. So we're going to suppose the contrary. We're going to suppose the closure of S is not a subset of L. So if we were to suppose the contrary, what does it mean for a subset to not be what does it mean for a set to not be a subset of another set? Well, let's derive what that means based off what it does mean, based off of what it does mean for the closure of S to be a subset of L. Well, if the closure of S is a subset of L, then that means that every element in F, the closure of S, is also in L. So if the closure of S is not a subset of L, that means that there must exist, so this implies that there exists an X in the closure of S that is not in L. Now, if X is not in L, then this implies that X is in S, and X is not the limit, as n goes to infinity, of an for some sequence of points that lie in S. So for some sequence A1, A2, A3, and so on. Now, when we're talking about sequences of points, we can actually translate this into the language of open sets. And you might be wondering, what do I mean by that? Well, there's three languages that we can kind of talk in. There are three languages that are useful to know when we're talking about convergent sequences, closed sets, and open sets. And that is obviously it might seem obvious, but the language of open sets, the language of closed sets, and the language of convergent sequences. And some statements might be really simple in the language of open sets, but might be really complicated in the language of closed sets, even though the two statements mean the exact same thing. They're just spoken in different languages. So we have a statement here in the language of convergent sequences, and our goal is to get into the language of closed sets, because that's where we have the most leverage for this particular problem, because we're dealing with the closure of S, which is the intersection of all closed subsets of E that contain S. So it might be helpful to convert this statement, X is not the limit of a sequence that lies in S. It might be helpful to convert that statement into the language of closed sets. But before we convert it into the language of open sets, before we convert it into the language of closed sets, let's convert it into the language of open sets. And then we'll go from there to the easy conversion from open sets to closed sets, because the complement of an open set, that is to say everything that's not an open set, is a closed set. So if X is not the limit of a sequence that lies in S, then I claim that this implies that there exists an open ball with center X that has no points in S. Now, why is this true? Why is this true? Suppose that this weren't true. Suppose that there does not exist an open ball with center X that has no points in S. And that means that every, so let me as a quick aside, this is our aside is going to be in pink here. So if this were not true, so let me say if the statement in blue is not true, if not true, then that means for every open ball centered at X, there exists points in S, in that open ball, Okay, so check out what this implies. Check out what this implies. If I have my point X, and I'm saying that every open ball centered at that point X contains points in S, then that means that if I take this open ball, and then I take an open ball of a radius smaller, and a radius smaller, and smaller, and even smaller, and so small that no matter how small I get, a radius as close to 0 as I want, I'll always be able to find points in that open ball. So check this out. I can create the following sequence where, check this out, I have an open ball of radius epsilon over 2, I have an open ball of radius epsilon over 3, I have an open ball of radius epsilon over 4, so maybe this is epsilon over 2, epsilon over 3, epsilon over 4, and then maybe epsilon over 5, this innermost, and then and so on, and so on. And in each of these open balls, there exists an x1 in S. I won't call it an x1, that might be confusing. I'll call it an A1 here in this first open ball, and an A2 in this other open ball, and an A3 in this open ball. And in each of these open balls, I'm always going to be able to find a point in S, even if it's the same point in each of these open balls, but eventually it won't. I'll leave that to you to convince yourself. But if I'm able to create this sequence where each of these points, A1, A2, A3, and so on, is in each of these open balls of decreasing radii. So check this out. I can say that this sequence converges to X because given any epsilon strictly greater than 0, given any epsilon, maybe I should have called these radii r over 2, r over 3, r over 4, and so on. But given any epsilon over strictly greater than 0, there exists an epsilon over n that is strictly, not an epsilon over n, an r over n, which is the radius of one of these open balls that is strictly smaller than that epsilon. So therefore, and moreover, there exists a point in this sequence that is in the open ball of radius r over n. So therefore, there exists, and moreover, every point after a sub n, and maybe I should have made this a capital N to be more in line with the definition of convergence. So every point after a sub n is in every open ball of radius smaller than r sub n. So check this out. For every epsilon strictly greater than 0, there exists an n such that r over n is strictly less than epsilon, which implies that all the open balls of radius smaller than r sub n have points in this sequence that are strictly smaller, have points in this sequence that are a distance away from X, strictly smaller than epsilon, because they're in an open ball of radius r over n, which has a radius strictly smaller than epsilon. So they're in a radius r over n, which is strictly smaller than epsilon. So that radius is a distance away from X, strictly smaller than epsilon. So therefore, all points in this open ball of r sub n, and all points in every open ball of radius smaller than r over n, are closer to X, which is the center of all of these open balls, it's closer to x than any point, that is to say, it's a distance away from x less than epsilon. So check this out. Therefore, if this weren't true, that is to say, if there did not exist an open ball with center x that has no points in S, then we would arrive at a contradiction. We would arrive at a contradiction. So this statement must be true. So I said all of that just to say that this statement, that there must exist an open ball with center x that has no points in S, I said all of this just to say that this statement is true, given this statement, that x is in S, and x is not the limit of a sequence of points that lie in S. So, check this out though. Check this out. I'm going to show the following thing. So let me clear some space here so that I can show my final point. So we just showed that there must exist an open ball with center x that has no points in S if given that x is in S and x is not the limit of a sequence whose points lie in S, which is true if x is in S, x is in a closure of S. So this statement is true. The statement in yellow here is true, given that x is in the closure of S, and it is also x is not in L. So check out what we can do. If there exists an open ball with center x that has no points in S, so I'll call that open ball with center x, I'll call that open ball B sub x. So then this implies that the complement of B sub x, and check this out, now we've translated from convergent sequences to open sets, and now we're translating from open sets to closed sets, and now we're almost at the end. We're almost at the punchline. And again, we've only proven part 1 here. I'll do it part 2 in a separate video. But we've proven we've now not yet. So this complement of this open ball, check this out. This complement of this open ball contains S. And why can I say that? Because the open ball with center x has no points in S. So, the complement of this open ball contains S. And not only that, the complement of this open ball is closed, because the complement of an open set is a closed set, and an open ball is an open set. So this guy is closed. This is closed, again, because an open ball is an open set, and the complement of an open set is a closed set. So this is closed. Not only is it closed, it's a closed set that contains S. Therefore, check out what we have. We have that x is in the closure of S, which implies that x is in the intersection of all sets G alpha that contain S. Not only all sets of G alpha, all closed sets of G alpha. All closed sets that contain S. So I'm just making this collection of closed sets. This collection of closed sets is all closed sets in the metric space E that contain S. So therefore, this complement of this open ball is in this collection of all the closed sets that contain S. So therefore, since x is in the intersection of all of these closed sets that contain S, then therefore x is in each one of these G alpha, and therefore x is in B alpha, the complement of the open ball centered at x. But this is a contradiction. X is in the open ball centered at x. I've just arrived at a contradiction. So this is a contradiction. X can't possibly be in the complement of the open ball centered at x, because x is obviously in the open ball centered at x. And the complement of the open ball centered at x contains all points that are not in the open ball centered at x. So this is a contradiction. And so check this out. If I were to suppose that the closure of S is not a subset of L, then I would arrive at a contradiction. So therefore it must be a subset of L. And we'll prove the second part in the next video.